Hello. So welcome to this session. We will talk about databases. You probably know SQL databases that have a lot of features, exist for a long time, but had some problem to scale out. Then you probably also know NoSQL databases, which kind of solved the scale-out problem, but removing a lot of features. And now we have distributed SQL databases, which tries to mix both, having a scale-out architecture where you have all SQL features on top of it. And one of them is YugabyteDB. I'm developer advocate for YugabyteDB. Actually, I've been always working with databases, mostly the monolithic databases, so vehicle Postgres. When NoSQL came, I was not really convinced for my consulting job because of the lack of features that we had on NoSQL databases, which means that you had a lot to do in the code for what the things that the database didn't do. And when I've seen distributed SQL databases, I was so motivated that I became a developer advocate for Yugabyte. Basically, distributed SQL databases started with Google Spanner. Same thing at Google. They used a lot of NoSQL databases with big tables, and then realized that you need more and more code to work around the fact that you don't have transaction, that you don't have strong consistency, and many things. So they started Google Spanner with the same architecture as their NoSQL databases, but with a few more SQL features to be able to do some relational table on top of it. Then came CockroachDB, TIDB, YugabyteDB. That's mostly what are the distributed SQL databases today. YugabyteDB goes a bit further in the SQL features. Rather than adding SQL features on top of the distributed storage, the idea is to plug Postgres, so a well-known, very popular SQL database, but plug it on a distributed storage. So my goal here is to explain a bit how it works under the hood. Of course, I can go in a lot of details or not. That will also depend on your questions, so do not hesitate to interrupt me. I don't know the level of knowledge you have on databases in general, on distributed systems, so please ask questions. This is how we will focus on really the things that you want to know in 1 hour. So starting with that's basically what does YugabyteDB. From the application, you connect as you connect to Postgres. Can use the same driver, the same syntax, and actually when you connect to a Postgres backend. But you can connect to any node, because the idea of a distributed database is that you run it on many nodes. And that's not like primary standby in monolithic databases. You have really many nodes that are active, and you can add more to scale out or remove to reduce the cost in the cloud, for example. So basically, the application connects us in Postgres, but the tables behind are distributed. So they are sharded, I will explain why, and they are also replicated, because the main reason to scale out is to have some redundancy, so that if one server dies, if one availability zone is not accessible, even if one data center burns, the idea is that the database just continues. The application doesn't see any error if one of the replica is down. And I will also explain that it's not the full database that is replicated in 2 or 3 points. The data is first sharded, partitioned in small chunks, and those chunks are replicated. So this is the idea where with those little cubes, the little chunks of data that are distributed. So let's look how it works. Basically, Yugabyte started with the distributed storage and then added Postgres on top of it. And most of my colleagues, the founders of Yugabyte, start with the distributed storage. I prefer to start from the application, because you connect to Postgres. And also mentioning that Yugabyte is fully open source. So all information, the architecture, all is public, the code, of course, also. So basically, if you know Postgres, which works like most other databases, if you know Oracle, it's very similar in this area. When the application connects, let me just put that. When the application connects, you have a process that is forked for your session, for your connection. So that's the first thing. And then you run SQL queries that are just text that must be parsed. And SQL is declarative, so you need an optimizer, a query planner that from the declarative language will build the procedural language to know how to get to the data, starting from which table, joining to which other table. And when the execution plan is built, then there is the executor that just executes the execution plan operations, like going through an index, going to the table, joining, sorting, doing all the SQL operations. Of course, this includes also running stored procedures, running analytic aggregates. All that is done by this layer. And then, when there is a need to write or read data, because the main reason for a database is to have data persistence, then it calls the system to write to files and read from files. And basically, the idea of Yugabyte was to get all the Postgres features, and there are a lot, just reusing the code of Postgres there and plugging the distributed storage at this level, where instead of reading and writing to local files, it will call the distributed storage behind. And Postgres is really nice for two reasons. First, it's open source, and it's very extensible. There are many points in the code that are defined place where you can do something differently. Ideally, you can do that with extensions. Here, I'm just simplifying the thing where we cannot reuse exactly the same code there, because, for example, when you build an execution plan, it must be aware of the cost of going to another server through network calls. So there are many places in the code. So basically, it's a fork of Postgres, but most of the code is the same as Postgres. So the idea of Yugabyte is to plug at this level. Instead of writing in heap tables and B-tree indexes, I don't know if you know the detail implementation of indexes and tables. In Oracle, in Postgres, the heap tables just means that when you insert rows, it can go anywhere in the table, and the indexes are B-tree organized on it. If you use MySQL, it's a bit different. The table itself is stored in the B-tree of the primary key. So basically, with Yugabyte, at this level, this is where there are calls to the distributed storage. And data is not stored as heap tables and B-trees because for multiple reasons, but one is that it's difficult to distribute because B-trees rely on the fact that you have blocks in memory. Basically, a database, you think of a database as reading and writing to disks, but actually it reads and writes to memory, to the shared buffers, and then goes to disk because not everything fits in memory. So in short, but again, ask question if you want more details, LSM tree means log structure merge tree. The idea is that the changes are not done in place in a specific block. They are just appended to a log. And so the first level, for example, if you insert a row in a table, this will go to the LSM tree, will be appended with the primary key values and all the row values, as the new version of the rows, the first version of the row. If you update, there will be a new append to this structure saying, for this primary key, for this column, the new value is this one. So everything is a log. And this goes first in the LSM tree, goes to a first level that is in memory. So that's fast. Very similar to Cassandra, for example, if you know, or RocksDB. So fast data ingest because you just append the log of the new values to memory. Of course, memory is limited, so usually this first level is limited to something like 100 megabytes in Yugabyte. I will explain why it is so small, because data is sharded, so it's not the whole table that goes there, just a part of the table. And the first level is in memory. When it is full, because it's a log, it's always appended, always increasing. When it's full, it is flushed to a file, SST file, sorted structured table file, that is just a flush of what you got there from memory. When I say appended in memory, it's appended but sorted by key. The idea is also when you read, you can find easily a key, the primary key, and then get the value. There is also a timestamp because you want a value at a specific version. And the file is quite the same. So basically, if you ingest a lot of data, it goes in memory, it's flushed to a file, goes in memory, flushed to a file, and because it's a log structure, this will always increase. At some point, that will not be efficient, so in the background, there is some compaction that will merge multiple files into one. Because when you read, you have a select for a primary key, a specific value, you have to go to the memory to see if it's there, but also maybe to the files there. So you don't want too many files, there is a background compaction on it. And basically, the idea there, so this kind of structure exists with RocksDB, for example, but is not really good for very large databases. So the idea is that the data is sharded. So a table is kind of partitioned on a hash value and the primary key, for example, or a range. And each shard will be its own LSM tree. So basically, for a big table, when you insert rows, that will be inserted in multiple tablets. I have more detail later about that. Just something to mention. This is the same structure for the table itself and the index. Actually, the table rows are stored in the primary key index, and you have secondary indexes that will store the index keys and the primary key to be able to get more columns from the table. Okay, and then I mentioned this sharding. In Yugabyte, those shards are called tablets. The idea is that a table or an index or a table partition, because there is also the Postgres partitioning, goes to a tablet. And this is what will be distributed. Of course, one row will always go to one specific tablet, but another row will go to another one. So the idea is that if for a table you have tablets in multiple nodes, then all nodes are working and you don't have a single bottleneck on one. And the sharding is done on the primary key for the table or on the index column for the indexes, either by hash or range. And I think I have examples just to explain the reason for them. So basically, because we use Postgres, we have the same syntax, but we have added the possibility when you define a primary key to mention that it is hash sharded or range sharded. There is a default. By default, the first column is hashed, which fits sometimes, but not always. So basically, if you move from a monolithic database to a distributed SQL database, you need to think about the sharding, depending on the access patterns that you will have. This is an example where I create a table. I also mentioned the number of tablets. You don't have to, because when data grows, the tablets will be split. But for example, if you know that you will load a lot of data, better to pre-split it rather than loading and waiting that in the background it is split. Even if it's online, doesn't block anything, it takes more resources. And basically, if you are hash sharded, you It's easy to distribute because there is a hash value, and then the ranges of hash value will go to different tablets. And it's easy to read when you have the exact value of the primary key. But let's say if you have an index on a value where you don't want to query on the exact value, but on a range, so higher than a value or between a value, then you cannot use hash sharding for that. So the case where you change the default hash sharding to range sharding is when you know that your access pattern will be on a range. Sometimes it's easy to guess on the data type. If I have a colon on a timestamp, I'm quite sure that people will query it on ranges. If I have a colon on a UID, I probably guess that it will always be an equality. So basically, in the syntax, you define hash with hash, and you define range with ascending and descending. So the same SQL syntax as with indexes, because the LSM tree can be ascending and descending. Just means that it is sorted and then have range rather than having a hash function before. Okay, any question for the moment? Yeah?
Can you actually select table even, let's say, I know in Cassandra you're limited by the data model, the way it's structured. The data model, you cannot do certain types of queries. Can you do that?
Yeah, I repeat the question for the recording. In Cassandra, where you have the same kind of structure to store and also some sharding, you have some limitation on the access patterns. Here, the difference is that the secondary indexes are fully consistent. When I said that Postgres is plugged on top of a distributed storage, this distributed storage is like a key value data store, but with transactions. So you can imagine the Postgres, the SQL layer on top of a key value data store, but that is fully consistent. So when you create a secondary index, so an index that is not the primary key, it is maintained and fully consistent. This is where you have the same agility as SQL. You don't have to change your code. If your query, you realize that your query is not fast because it doesn't access, because you don't have the right index, you just create the index for that. You don't have to change the code. And because there is an optimizer, a query planner, it will use the index. So it's always good to have an idea of the access patterns, but maybe not all the access patterns, just a basic idea about the keys. Does it answer your questions? Yeah. There is another question. Yeah.
Which isolation level was supported?
Which isolation level? So when you use a SQL database, you have transaction, you have full acidity, and you have isolation level. Basically, the main isolation levels are serializable, where you have a guarantee that you have no anomaly on race conditions. So that's the best because you don't want to test your application for everything that can happen with multiple users touching the same data. So serializable is kind of nice for that, except that if there is a conflict, you will get an error and then you have to implement a retry logic in your application. So usually serializable is quite nice for new applications, but the goal of being Postgres compatible is also being able to take an application written for Postgres and run it on Yugabyte without any change. So basically, Yugabyte supports the same isolation level as Postgres. You can choose serializable if you have a retry logic in your application, or you can choose read committed. Most of Postgres applications use read committed because it's the default, because it is easy. There are some possibilities of anomalies with concurrent sessions, but the application manages that with explicit locking. For example, doing a select for update or something like that. So here you have the choice. And basically, from the Postgres layer, the read and writes are sent to the tablet. And read and writes are not only the changes to the data, all the locks, the intents, the provisional records go there also. So if you are in serializable, even when you read, you send write operations to write a lock so that other sessions know that you have read this data and you want a consistent view on that. So yeah, same isolation levels as Postgres, that's the goal. And this is also mandatory to be Postgres compatible. For example, CrossDB is compatible with the driver and has a similar syntax, but doesn't have all Postgres features like stored procedure and doesn't have read committed. Here, the goal is really to be able to move an application from Postgres to Yugabyte. Let's say directly, not all applications, this is really optimized for OLTP. If you are building a data warehouse, you probably don't need those transactions, and you probably need more aggregates, and there are other solutions. So do not move any application from Postgres to Yugabyte just to distribute it. The main optimization is for OLTP. Everything works, but for performance, for the moment, there are many aggregations that are not pushed down to the distributed storage, which means that in this architecture, if you do a complex query with group by, sums, average, then the risk is that if it's not pushed down, you will read a lot of rows that will go to the Postgres backend, and then only one process will do the aggregate. So a few aggregates are pushed down, not all of them. Yeah? Yeah. So the question is, you have an option of explicit locking, either with lock table or with select for update, mostly. Yeah, this works also. And there are two kinds of locks. For the moment, the pessimistic locking is still in preview, which means that you have the same behavior as locking, but behind it is not rating, it is retrying internally, which is possible in read committed. And we have in preview, we have implemented wait queues with detection of deadlocks, which probably will have the best performance for most cases. But yeah, you can do select for update, you can do select for update, skip locked when you have something like a queue. So basically the idea is that all Postgres features are supported. If it's not the case, maybe there is a Git issue and it is in the roadmap, or open a Git issue. There are a few DDLs that are not supported yet, like the alter table that changes the data types or things like that. The problem is that everything that is implemented there must be scalable. Makes no sense to lock a whole table on a database that is built to be scalable and fully online. One reason to scale out is also to never stop the database. For the upgrades, you just upgrade one node after the other. You never stop the database. So the features that can be tricky to do without stopping the database need still to be done. So basically, those shards are tablets and are replicated with the Raft algorithm. The idea is that all the reads and writes to a specific tablet will go to the leader of the tablet. So for one row, it will go to a specific leader of the tablet. Another row will have another tablet, and then elsewhere. The idea is that if you read and write from the leader, then you have consistent reads and writes. If you have also the possibility to read from a replica, but then you cannot be sure that you have the latest writes. What Cassandra does is that you can read from multiple replicas, but here the idea is also to have good performance for reads, so reading from only one place. So basically, when you write, it writes, so sends this append log to the LSM tree in the leader tablet, and that goes to memory, is protected by write-ahead logging in case of failure there, but this log is also sent to replicas. Typically, a production will have replication factor 3, and then each leader will have 2 followers. And it waits for the quorum. The idea for the best performance, of course, you have to wait if you want to be sure that if this one is down, you have the latest data elsewhere. But we don't want to wait for all replicas, only the quorum, the majority of them. Which means that if the node that has this tablet leader down, those two can talk together and know which one has the latest value, because they acknowledge all writes on a quorum. And when you read from the leader. That's already quite well distributed, except, of course, if you update always the same row. But this never scales. It's just worse if you do that on a distributed database. There is also the possibility to read from the followers if you accept stale data, because the followers may not have the latest writes, but they know if they have the latest as of a few seconds before. So for reporting, for example, you just set your transaction read-only. You know that you will not write anything, and you accept a staleness of 15 seconds, and then you have a consistent view, but as of 15 seconds before. That's, for example, to distribute more the reportings. So basically what we see there, read and write to the tablet leader. There is an additional change data capture from there. The idea, the big difference with the monolithic databases and the primary standby configurations is that in traditional databases, everything about replication high availability has been added on top of it. First, you had the write-ahead logging, redo logs added to protect from an instance crash, and then it was used to get recovery on backup, and then it was used to send to a standby. Here, the idea is that everything is built in the database, and at the same level, the changes, the key value changes, are used for change data capture, for replication, for all of that. And and the possibility to read from the followers if needed. Yeah. Yeah. So you have leaders everywhere, and then you have a leader election in two cases. First, if a node is down, then the leaders that were there are not accessible, and then the followers will elect a new leader. And that happens in a few seconds. Actually, it happens immediately. We just do not trigger it immediately, so there is a configurable timeout that is by default after 3 seconds. And then immediately reads and writes are available on the new leader without any data movement. They just have to talk together. One follower doesn't know if it has the latest change, but if it talks to the quorum, then the quorum knows which has the latest change. So leader election can happen in case of failure, or just because you blacklist a node because you know that you will stop it, for example, or the cluster can automatically decide to add more replicas and elect new leaders to distribute the load. Because one goal is high availability. For example, you deploy in the cloud on 3 availability zones, so that you are sure that you have a quorum. If one availability zone is not available, you will have leader election so that everything continues on the others. But you want also elasticity, like adding more nodes because you are retail, and in November, December, you know that you need a lot of more, you have a lot of more activity on it. So for elasticity, you add new nodes. So you scale the infrastructure, and you have nothing to do on the database level because the automatic balancer will detect that it has nodes without any replica. So we'll start to add new followers there, and then we'll realize that there are nodes with no leaders, and then we'll elect leader on it. Basically, I didn't mention you can deploy it on anything where you have Linux, so can be VMs, can be containers, can be Kubernetes. If you scale the stateful set in Kubernetes, you just do that, nothing on the database, and immediately the database will start to add new replicas on the new pods. So it will be able to already get connections and have data there. Of course, if there are terabytes to rebalance, the full rebalance will take a few hours. There were another question, yeah? Yeah, very good question. What happens, because most of the failures are transient. I mean, a data center can burn, but more frequently, the network is not accessible. So let's say that you have the leader that is not accessible, so tablet, the followers elect a new leader there. If it's back, by default, we keep 15 minutes of those logs. The leader keeps 15 minutes of those logs. So if this one comes back and still has data, because it was a network error, it was not a disk error, then it can just catch up with the latest changes if it comes back within 15 minutes. After 15 minutes, and this is a configuration, but the idea is that after 15 minutes, we don't want to keep hours or days of changes. So if the node is down for too long, then it is just out. And then if it comes back like a new empty node. And it will have to bootstrap the replicas from the others, so with a full copy. So you have short failures, then it catches up the latest changes. Longer failure, then it's just a node that disappeared. Yeah?
One question based on this, do you need even count of nodes? Or
Yeah, good question. The number of nodes. So for the quorum, you need an even number. But that's not really nodes, it can be zones. For example, if you deploy on 3 data centers, 3 availability zones, you can have 10 nodes on each. But the idea is that you have 3 zones. Basically, when you start a new node, you tell it in which zone you are. There are tags for zone, region, and cloud provider. So basically, you define the level of protection you want. When you deploy, you know if you want to be resilient to one availability zone failure within a single region, but you can also deploy in multiple regions. And then when it is tagged, the database, when it rebalances the leaders and the followers, ensures that it doesn't put the followers on the same zone. Can be also multi-cloud. For example, you can have some nodes on Azure, some nodes on AWS. So either because you want to run like that and have the money to run like that, or just because you want to move. And then you start new nodes on another cloud provider, and there is rebalancing, and at some point you can blacklist the other ones and go there. So the idea is to have a lot of flexibility there. And of course, if you go multi-region, then you add some latency. When you see that you read from the leader. So when you are multi-region, you can also define the placement of the leader for specific table or specific table partitions. For example, you are a bank and you want your European customers to have their data in Europe. So you can partition the table on the country and then define the placement for this table to a specific cloud region, for example. So this is how you reduce the read latency. Writes will always have to go to get the acknowledge from one of the follower. So you don't want that to be other in 100 milliseconds or too much. So there are some deployments in multi-regions where you have 2 regions nearby. You place by preference the leaders on those 2 regions that are not too far, and maybe 1 region that is a bit... in Europe, it's easy because all cloud providers have many regions. But in US, for example, it's difficult to have 3 regions that are not too far. But 2, yeah, you can. So, yeah, that was I don't remember what was the question, but I probably answered it. I went a bit further about the placement and the multi-regions, but the idea is that you have the flexibility. If you are in a single region, I will not say that you don't care about the latency, but for example, if you are on AWS, I don't see a latency difference within the same availability zones or zone or between multiple availability zones. So you don't really care about the latency there. If you go to multiple regions, yeah, of course, you may have. And then the full picture, I don't know. No. I wanted to go to the next one. Yeah, the full picture of a deployment. So what I tried to put there is multiple nodes. Look only at the bottom, the YB tablet server there, where you have the tablets. And what I tried to put is that the full colors are the leaders and the hashed colors are the followers. So the idea is that this is distributed. Maybe the same table will have a tablet for a few rows hash value on one node and a follower there, a follower there. And basically, if this node is down, then one of those two followers will elect the new one. If you add a new node, then it will bootstrap a new follower from one of the other and maybe elect a leader on it. So that's the T server for tablet server. In addition to that, in a deployment, you have also a master, which is a term that I don't really like because it's not a very important component, it's just the cluster metadata. So if the master is not available, everything runs. It's only that the rebalancing, for example, will not be done. And this one doesn't have to scale more than the replication factor. So usually you have many nodes, and the master is just one tablet for the cluster metadata that is also replicated to be highly available, but you don't need more than that. Just to mention, I think I have a slide after about the Kubernetes deployment, but mentioning that you have two stateful sets, one with the tablet server, the one that you want to scale, and one for the master, just because it must be placed in the right zone, but it's not so important. Yeah? There is a limit of leaders per node. Basically, those are soft limits that are defined by the configuration. The idea is that, so there are many things that are configurable because there are many different applications. People who build an application today for a distributed database will probably build something with microservices, having a few tables. But when you start to be Postgres compatible and telling people that they can move their existing application from Postgres to Yugabyte, then you can see everything. Then you see applications with hundreds or thousands of tables. For example, Timinos is a well-known banking application. They have 60,000 tables. Not all full, because it's a software with many modules, but there is a lot. So of course, the number of tablets per server must be controlled. What we do for those applications with many small tables is the possibility that many tables can be co-located within one tablet. For example, if you have many lookup tables, you want to collocate them first because you don't have the overhead of thousands of tablets, but also because then you don't have network calls between them. If you have a join between 4 small tables, like 4 dimensions and one fact table, at least those 4, you don't want to add latency between them. So about the number of tablets, there is an auto-splitting job that will split your table or your tablets to more tablets when the table grows. And the targets are try to have tablets that are not more than 10 gigabytes. It works also with 100 gigabytes, but the goal is not to have too much. Basically, the storage is based on RocksDB with a lot of changes. And 10 gigabytes, 100 of gigabytes, is okay for this kind of structure, but also when there is some data movement, adding a new replica on a new node, a small chunk of 10 gigabytes is easy to move. You don't want an operation that moves terabytes. So it's more the size of the tablet, and then the number. Yeah, something important. Each tablet is a Raft group. Each tablet is really independent in its replication. So it sends heartbeats to the other, it has its own memory, and then you don't want too many of them. Depends on the number of vCPU that you have in the node and the memory, but you don't want 10,000 of tablets, because maybe you will have vCPUs just sending heartbeats to the others. And yeah, that's a bigger picture where, in addition to a cluster, we can also have read replicas that are kind of the same followers, but that do not participate in the quorum. The idea is that if you have a cluster in Europe and some people are doing some reporting from US, it's okay that they have a read replica, but you don't want that in case of failure there, you wait for a quorum from there. So just to mention the flexibility, the basics of the replications are in the Raft replication, and then there is flexibility in the placement of the leaders and the followers. Let me look at the time. I will go fast on that because I already mentioned that you can partition, and this is also why the tablets, I call that sharding and not partitioning, like in Cassandra, for example, because in Postgres, we have partitioning. And we use partitioning if, for example, if you want to place specific data on specific regions. So you have those two levels. The sharding is really there to distribute, and the Postgres partitioning is used more to put specific data placement. Same, we are using the Postgres table spaces. In Postgres, you can define table spaces to go to a specific file system. Here, you use table spaces to go to a specific zone or region or a cloud provider. So this was just to mention that you have those two levels, and the partitioning at Postgres level, you have only local indexes. But the sharding, all indexes are global. So that's also very important and probably different from many NoSQL databases. You can really have many global indexes that are still distributed. Here I have more information about the details, but I already mentioned a few things, that the writes are appended as a log sequence to memory, and then it goes to files that are compacted in the background. And the code base for that comes from RocksDB with a lot of changes. There is a difference, of course. Don't build the database from scratch, so it reuses code from many other projects. The Postgres code reuse, the goal is to stay compatible and merge the new version of Postgres. Here, the code from RocksDB was used, but with no goal to merge from RocksDB. It was just to start with it. Same as for the Raft algorithm. The code base is from Apache Kudu, because that's a nice implementation of it. And yeah, one more detail there. When I mentioned that each tablet is a RocksDB database, LSM Tree, actually, it is two databases. Because in SQL, you have transactions that can do a lot of operations. So it goes first to an intent DB as provisional records. And at commit, it is marked as commit, so already usable. And in the background, those intents will be applied to the regular DB. The thing is that in a SQL database, you need to have the visibility timestamp for the rows when it was committed, but you don't know the commit timestamp before the end of the transaction. So you cannot directly write rows with their visibility timestamp. So this is how it is done there. It goes to a temporary database with the provisional records, and that commit, it is moved into another one. So just to mention that there are two databases behind it. Probably the one with the provisional record will never be flushed to a file. because by default, the memory table, the first level is 100 megabytes, and except if you have very long transactions, it never goes there. So it looks like an additional database, but it's just a buffer that is protected, of course, and replicated also. And then I mentioned, yeah, so the reads have to read from the instance DB and from the regular DB. And if it's from the instance DB, must see the transaction status, know if it is committed or not. But this is fast because it's probably in memory. And then read from the regular DB, from the memory table, and from the SST files. In addition to the fact that they are compacted, there are also a lot of improvement in the RocksDB code to have index, kind of index, Bloom filters, to know that for a key, you don't need to read all the files. And read all the files when you read with a key, so an index access, you just go directly to the key. You don't have to scan everything. Okay, is there any question on that? Yeah?
I have a question. How conflicts are resolved in my previous case that I mentioned? When the leader comes back, and you have some rights, right, and you have some rights here, and there may be conflicts. And another one is how sensitive is having nodes like in different regions, and how big of an impact of latency?
Yeah, okay. So 2 questions. The first one is about when a leader is down and then is back, you have always one source of truth for one row, and it's the leader. So you have no conflict. It is synchronous replication. If I update a row, I'm connected to a node. If this node is down, I have to reconnect to another node, of course. If I'm connected and I'm reading data, it reads from the leader. If the leader is down, I will read from the new elected leader. And the write will go to the new elected leader, so you never have conflict. We keep the logs only to catch up the changes, but it's still a follower. So if a node is down, the leader there is not accessible. There is a new leader election elsewhere. When the node is back, it catches the changes, but it's still not available. When it gets all the changes, it becomes a follower, and then can be part of the quorum, and maybe it is elected as a leader, but only when it is sure that it has the quorum and the latest changes. So the replication is synchronous, but synchronous to a quorum. But yeah, replication is synchronous. On top of that, between 2 clusters, we have the possibility to do asynchronous replication. Using the same logs, but in a synchronous manner. For example, you use that if you have regions that are really far and want to do disaster recovery with that. But also, there are many on-premises. There are many companies with 2 data centers on premises. You cannot have a quorum with 2 data centers. So in this case, the correct deployment is to have a cluster on each data center to be resilient to node failure, disk failure, and on top of it, have asynchronous replication between the 2 data centers in case of disaster like a data center that burns. But it's on top of it. The basic replication here for high availability is synchronous. Yeah. And the second question was about, there are 2 things about the time when you go to different regions. One is the latency. So the worst you can do is deploy on multiple regions with 100 milliseconds between them and do not care about the placement, and then join many tables that will have to read from many places. So the first thing is having all SQL possibilities and scale-out possibilities doesn't mean that you have to do the crazy thing of both. So if you have SQL queries joining 10 or 20 tables, then probably you want those tables to be collocated at a specific place, at least their leader. You can do it, but then you add latency. And so you do not reduce the latency. Yeah, you reduce the latency with the placement. What the database does is batching as much as possible. So of course, from the application, if you have 100 rows to insert, if you insert it in one statement, the database will send it as a batch to the follower, and then you will have only once the latency. But if you insert it row by row, you will add the latency for each row. So the database itself tries to batch as much as possible, not to multiply the latency by the number of rows. But from the application point of view, basically, a bad design on a monolithic database will be worse on a distributed database because you add the latency. But the best practice, the recommendations are basically the same. It's just that the impact is higher. If you read too many rows in Postgres, you will use CPU to read from the shared buffers. Here, you may go to another node, so it's just add. And something else that maybe is mentioned there, there is also something when you deploy on multiple nodes. I mentioned that there is a timestamp, like the commit timestamp, because in SQL, you want a consistent view, and then you have many changes on different tables, so different tablets, but at some point, you need to see all data as of a specific timestamp. So you need this timestamp. And for that, we use the physical time of the servers, but that's not sufficient because physical time can be different. That's the clock skew. So there is also the Lamport algorithm that synchronizes a logical clock on top of it. And if by chance or because you are not lucky, you are reading rows that come from different nodes that never exchanges a message recently, their logical clock is not synchronized, and then there is a possibility where the clock skew is detected, means that the server may be more than a few hundred milliseconds with a different time, and then we cannot guarantee the consistency, and then you get an error, and it is retried. If it can be retried automatically by the database, it is. If not, it is not. So there is also this, and that's the main difference with Google Spanner. Google Spanner has the same architecture, not using Postgres on top of it, but the same architecture for the distributed transactions. Big difference is that Google Spanner runs only on Google Cloud, where they have atomic clocks. And then they know that the skew is very small. And then what they do, they rate this possible skew for each write, because it's small. We cannot do that because if you deploy multi-region, the difference between the NTP time can be 500 milliseconds, so you don't want to weigh that. This is why there is the Lamport algorithm and the detection.
Using time is, of course, to scale versus using the version, like other.
Yeah.
Is anybody else, like competitors, they use?
Yeah, that's a good question. I think TIDB, which is the same kind of architecture but more MySQL compatible, I think they use a single point for the time. But here the idea is that everything can scale, and yeah. So this is why, and basically this works quite well because the servers exchange messages between them. So the Lamport algorithm synchronizes the clock quite good usually. Okay, 5 seconds remaining. We'll skip that. It's about the time. I mentioned it. Leader follower, we mentioned it a lot. I will just show an example if you deploy on Kubernetes. So you have a stateful set for the tablet servers, this one that you can scale. So the idea, the database distributes the data, so you don't need a shared storage. When you deploy on VM or pods here, you have a persistent volume for each node. When you add a new node, you have a new volume for it, and data is rebalanced between them. It makes no sense to put the data on NFS, for example, because the database distributes already the data. You don't want to add more latency on that. So that's basically the tablet server stateful set. And you have also a stateful set for the master, but that you don't need to scale, and that is small. And it will just go on some pods. Of course, there are some affinity rules that are defined so that you don't have all pods for multiple replicas on the same node. And if you deploy multi-region, you may decide to have one stateful set per region if you want. The only thing important is that they can communicate within each other, so through private network or public network, and that they can communicate with the master. And just to mention that the database is fully open source. The Yugabyte company just does support, managed service in the cloud, and also with the support, you may have a tool that is not open source to do more the DevOps part, more automation. But the database itself is fully open source. So basically, the Yugabyte company is only service, not software. And that's mostly all, with one additional thing. The beauty of this architecture, where you have distributed storage and transaction layer, and on top of it, the SQL layer. And between them, there is an internal API, those key value read-write operations. This architecture allows multiple APIs. So Postgres is one of them, because today distributed SQL is really where people want to go. But you can also use a Cassandra-like API if you want to. The performance and the features, well, the performance is the same, the consistency is the same because the storage is the same. Basically, where you may prefer the Cassandra-like API is if you have an application that uses the drivers. The Cassandra drivers talk directly to the different nodes, where the Postgres drivers connect to a specific node to get a backend there. Okay, I think we are on time. Do not hesitate to contact me. I'm a lot on Twitter, but I'm easy to find, and it's open source. Everything is on GitHub. And the reason to be open source is also to get feedback. When you want to be Postgres compatible, you also want the feedback from people saying, I have my application in Postgres, I tried it in Yugabyte, it works like a charm, or it works but it's slow, or I have errors. And then this feedback helps to improve the product. And if you have any other questions, I'm there all day, so I think we'll stop now. Thank you very much.